Hello everyone. We are on section 6.4. So we're picking up now with the last two sections of chapter 6. And here we're going to be talking about electronic structure of atoms to start. So these are also known as electron configurations. So in this section, we are going to derive the predicted ground state electron configurations of atoms, identify and explain exceptions to predicted electron configurations for atoms and ions, and relate electron configurations to element classifications in the periodic table. So this is where all those N levels and L and ML, MS, all that fun stuff comes into play, and how we use it. So just to kind of give you a little refresher from last week, when we have that principal quantum number of n, okay, then that tells us our energy level that an electron is at. And we have the angular quantum number, which is L, and L goes up to n-1 in value. We had the magnetic quantum number M, okay, or M sub L, and it goes from negative L, 0, all the way to positive L. And we can use that to make orbitals, a combination of N and L. So 1s orbital is an N equals 1, L equals 1 represents the S subshell. So we did all these. We filled out a little table as well in our examples. So just to kind of refresh your memories, because I know everybody totally watched all the lecture videos last week. Cough, cough, I saw the YouTube views. All right. So let's talk about these, starting off with what electron configurations are. So remember, as we increase that principal quantum number n, we are increasing the energy of our atomic orbitals. The higher the n, the higher the energy. As that n goes up, the size of our orbital increases because we're adding more shells. And our electrons are now spending more time further and further from our nucleus. So now that attraction to the nucleus is weaker because we're further and further away from that positive charge. So you've got your nucleus here, and more energy levels we add, the further we're getting away from the nucleus. So further distance, higher energy of these orbitals. So they're less stable. Keep that in the back of your heads for next section. So once we start getting atoms with 2 or more electrons, so not hydrogen and not ions, and not ions with only 1 electron, we start getting repulsion between electrons. So that is going to give us these different values of L. And as we add more L values, the energy also increases within a shell. So just because we're at n equals 2, okay, now we have 2 L values, 0 and 1, we are still going up in energy. So S, okay, L equals 0, is the lowest energy, then P, then D, then F. So electrons want to go generally to the lower energy orbitals first. They want to be nice and stable. Okay? Generally, things don't want to go to higher energies unless they have to. So this is an energy level diagram. I'm going to have this up multiple times, but this gives you an idea of how the orbitals go up in energy. So 1s here is at the bottom, so the electrons are first going to go there, and then to 2s, then to 2p, 3s, 3p, And then one thing that happens, we'll talk about this a little later, is it goes to 4s and then 3d. So the 4s shell is actually lower in energy than the 3d shell. So that's something to keep in mind. So, but you can see the order of how these orbitals fill up. So we go from the lowest energy and we slowly make our way up, but still filling in the lower energy subshells as we go along. And each blank there represents 2 electrons, or can hold 2 electrons. So how these electrons are arranged is called the electron configuration of the atom. So it has symbols with 3 pieces of information. It tells us the quantum shell N, the orbital in the form of sp, d, or f, which is L, and a superscript that tells us how many electrons are in that subshell. So we'll look at some examples which helps really be able to visualize this. So here's the hydrogen atom. And what we do is, so keep that electron energy diagram in the back of your head. Hydrogen has 1 electron. So that 1 electron would go into the 1s subshell. So that is the 1s here. And then we're done with all the electrons from hydrogen. There's no more. So then we do the superscript with the number 1 to say there's 1 electron in the s subshell. So you can kind of read this backwards. There's 1 electron in the s subshell at the n equals 1 energy level. So to get the full electron configuration of an atom, we need the number of electrons. For a neutral atom, remember the number of electrons are equal to its atomic number, aka the number of protons. So as we continue across our periods of the periodic table, we add an electron to the subshell of the lowest available energy. And this is called the Aufbau principle. Okay, so this is German from the word Aufbau, to build up. And we also have to keep in mind the Pauli exclusion principle, which, remember, tells us there's only 2 electrons per orbital. Okay, or per suborbital, if you want to say it. Okay. So I love to use these diagrams. They're very helpful for doing electron diagram or electron configurations because you can kind of fill it in first, and then you can go and write your total configuration. So let's find an example that I like. For instance, let's do carbon. So carbon has an atomic number of 14. So that means we have 14 electrons. So we're going to first start with the 1s diagram. And we're going to look at actual orbital diagrams later. But the way that we denote this is we do 1 electron with an arrow pointing up, and then the 2nd electron pointing down, because that's from the those quantum spin numbers. They have to spin in opposite directions when they are paired off. So now we've filled up the 1s orbital, 2 electrons, Pauli exclusion principle. So now that's 2. So now we have 12. We're going to move up to the 2s diagram. 1, 2. That guy's full. We have 10. Now I go up to 2p. And when we fill these in, we first want to fill it in so there's only 1 electron per space. Think of it like getting on a bus. In general, you don't want to go sit next to a stranger on a bus, right? So first, all the single seats fill up. And then, once they're full, then you have no choice but to sit next to some stranger. And just hope they don't fall asleep on your shoulder. So there's 6 electrons. So now we have 4 left. So now we're going to move up to the 3s shell. 1, 2. And now we have 2 electrons left, so those are going to go in the 3p. And we're done with our electrons. So now the next part is to write our actual configuration. So this goes 1s, and in that shell there's 2. to 2s, 2, to 2p, 6, 3s, 2, 3p, 2. And then we're done with that configuration. And that is the electron configuration of carbon. This is another way you can visualize the order for our orbitals. So again, if we were to do carbon, okay, again, 14 electrons, you start at the top and make your way down. So it goes, okay, 1s, and then we go to 2s. Then we come up 2p to 3s. And you have to make sure you're counting as you go. There's 12, and then boom to 3p is where we end, 3p2. So this is just another example, another way that you can visualize this. So this is a great also example of the electron configuration for each subshell. You can see that certain areas have certain electron configurations. For instance, groups 1 and 2 plus helium are all blue, and these guys all end in the S subshell. So this part of the periodic table is called S block, because when you do their electron configurations, they end with an S in the S subshell. Over here in orange, we see these guys all end in P. 2p, 3p, 4p, 5p, 6p. That's their final orbital. So this is called P block. You will never guess what the transition metals 3d, 4d, 5d, and 6d block is called. Yep, you're right. It's D block. And then our green guys down here, 4f and 5f, these are called F block. A little later, I'm going to talk about how you can use these blocks to your advantage to either predict an element if you're given the configuration, or actually figure out the configuration also. So we talked a little bit about orbital diagrams. I showed you the big diagram, but what an actual orbital diagram is, you make your own little boxes of your individual orbitals and fill in the electrons. So for hydrogen, 1s1, okay, it's got that one cute little electron. And we use the half arrow pointing up to represent a spin, quantum spin of plus 1/2. And then if you have maybe a helium, which is 1s2, then you add that down spin, which represents negative 1/2. So that's what those up and down arrows represent. So this is how we make these orbital diagrams to go with our electron configurations. You draw the little boxes. Okay, for the S orbitals, you only need one box. Each box holds 2 electrons. Okay, so for things like helium, lithium, beryllium, you only need 1, maybe 2 boxes if you have the 1s and or the 2s. And once we get to something that has the p orbital, something like boron, hope this isn't too boron for you, you need to do 3 boxes that are connected. Because if you remember, the 2p orbital, okay, that's L equals 1, so ML equals -1, 0, and +1. That represents the 3 parts of the p subshell. So that means the p orbital can hold 6 electrons because it has those 3 nodes in it. So we have to do 3 boxes. And we see that boron, though, has 5 total electrons. 1s fills up first, then 2s, and then we have 1 lone electron here in the 2p orbital. So the reason we do this is called Hund's rule. For carbon is our first example where we see this, where if you have degenerate orbitals, the lowest configuration is having as many unpaired electrons as possible. So for carbon, Hund's rule would be that we have 2 unpaired electrons in the 2p orbital. Okay? So 2 seats on the bus, each with 1 person in them, and then 1 empty seat. So these electrons are spinning parallel to each other. That's the other thing to notice. They are not spinning in opposite directions. They are parallel, same spin. Here's a few other diagrams for you. Nitrogen, notice now we have 7 electrons. So now we've got these 3 unpaired electrons. Then we add 1 more electron to go to oxygen, and we have to now start pairing. Fluorine has 2 pairs. And then when you see neon, neon is a noble gas. It's not our first noble gas. That would be helium. But neon has this nice full 2p orbital. Okay, notice there's really no room for electrons to enter. Okay, this is why noble gases are stable. They have a nice stable electron configuration. So this is also why our metals and nonmetals either lose or gain electrons, because they want to have the closest configuration to a noble gas. So they will either lose electrons if that's easier, or gain electrons to have a noble gas electron configuration. So the electrons that are in the outermost shell, so the highest value of N, are called valence electrons. And these guys are the most important electrons because these are what actually participate in chemical reactions. Okay, these are what are lost or gained. They're what's shared for a covalent bond. Okay, valence electrons are the most important part of our atoms when it comes to chemical reactivity. Whereas the inner orbital electrons are called core electrons. Okay, so just think of like an apple core, right? You don't want to eat the core of an apple. I mean, I've known people that do. My boyfriend may be one of them. I don't know either. You want to eat the outside, meaty, yummy part of the apple, right? The valence electrons of the apple. So now these core electrons, these are full shells and or subshells. And these represent noble, or not subshells, sorry, these are full shells. And these represent noble gas electron configurations. So these are, very close. These have the electron configuration of a noble gas, plus then you have those extra valence electrons now around it. So, as I say, chemists are lazy. So here's our lazy chemist time. So what we do is we use the noble gas that matches the core electron configuration and abbreviate that for those core electrons, and then we add the extra valence electrons. Okay. Okay, so just a little reminder too about this periodic table. This will come up again a little later when I talk about some shortcuts. But our noble gases, just to remind you, group 18 or 8A, however you want to look at it. These guys, they are in P block, which means they have a full P subshell. So these are going to be the ones with a nice full valence, nice stable atoms. So here's an example of going from a full configuration to an abbreviated configuration. Sodium here has 11 electrons. And when we start filling it in, 1s2, 2s2, 2p6, this is the same as neon. Okay, so neon is right before it. Element number 10, it's a noble gas. So that is the closest noble gas to sodium. So we have neon and then 1 extra electron, a valence electron of 1. Also keep in mind that's group 1A or group 1, depending on the numbering you want to use. So our valence electron is, we have 1 valence electron here. So we are in the 3s shell. That is our outermost shell here. And there's only 1 electron there, so we have 1 valence electron. So you can write this either way, either the expanded configuration or the abbreviated version. They mean the same thing. Okay, so here's that electron capacity chart again. I just thought I'd show you a little bit of the grouping of our atoms, how it works. So for instance, lithium here, notice it goes helium 2s1. So helium is 1s and then 2s1. And notice then we have one valence electron in an s orbital. And then as we add again for sodium, we end in 3s with one valence electron in an s orbital. Then we move up to potassium, which has argon, and we end in the 4s1 orbital. Notice 4s starts to fill up before 3d because it's actually lower in energy. So the highest energy level is 4, and it has one valence electron. So notice for all of group 1, we have one valence electron. For group 2, if we were to do the same type of thing, what we notice is they have two valence electrons. So beryllium is our first one, 2s2. So we see we have two valence electrons. We're filling up the s shell first. And then magnesium goes to 3s2. And argon goes to 4s2. So again, two valence electrons in the s block. Okay? So now we see these similarities in valence electrons. And we had talked way earlier in the semester about similar reactivities of, for instance, all the group 1 elements, all the group 2, all the group 17. These similar reactivities are because of these valence electrons. They have the same number of valence electrons. Okay. So this is another periodic table version. And this actually tells you the electron configuration of each element. I know it's kind of hard to see on my screen, but it's in your book, whether you have the physical copy of the book or you're just using the internet copy, which you can probably zoom in on a lot better. But this gives you the outer shell electron configuration. So basically, let's say I want to know the electron configuration for nickel here. And I look and I see that's 4s2, 3d8. And then well, that's an awful looking 4. Let me fix that. And then I need to figure out what comes before it. I go, okay, I'm going to trace back argon is going to be my noble gas that my core electrons have. And there you go. So let's talk a little bit about transition metals with their electron configurations. The S block and P block elements are pretty straightforward with their configurations, aside from like the 4s filling up before 3d, but even then, keep that in mind and you're fine. All right, so starting with atomic number 21, which is scandium, electrons start to be added to the 3d subshell. And these subshells can be filled up to 10 electrons. Okay, so if we have L equals 2, that represents the d orbital. We have 2L plus 1 equals 5 values of ML. Because we can go -2, -1, 0, +1, and +2. So each of them can hold 2 electrons. That means a total of 10. After we fill up 3D subshell, then we move up to the 4p subshell. So this goes 3s and then 4s, and then to 3d, and then to 4p. And this comes from 3p. Now we also have the inner transition metals. So those were the D block transition metals, and now we have the F block transition metals. These are the 2 rows below the periodic table. These are lanthanum through lutetium and actinium through lawrencium. These have an F subshell, and this is L equals 3, which have 7 values of ml, meaning a capacity of 14 electrons. It's a lot of electrons. So just another little thing. When I was an undergrad and in high school and stuff, and we studied, and people would ask, well, why are those 2 rows on the bottom? And most people would say, oh, because we're lazy and we wanted to make it fit. There actually is another reason, and that is because these electron configurations end in the f orbital, whereas the others in the regular transition metals end in the d orbital. There are some exceptions, like copper and chromium. Sometimes they prefer to be half-filled. For instance, copper, you would expect to have the argon configuration, then go 4s2, 3d9. But in reality, 1 electron from the s orbital jumps to the d orbital to fill it up, and it's 4s1, 3d10. I don't really expect you guys to remember this. It might pop up on your homework, though I'm pretty sure I filtered these out. It's just I just want you to see that there are exceptions, because atoms are weird. So let's look at an example. We want to figure out the electron configuration and orbital diagram for phosphorus, and then the 4 quantum numbers for the last electron. All right, so the first thing is to find phosphorus on our periodic table, and we see that phosphorus is element number 15, which means we have 15 electrons. So that means we have to fill up 1s2 first, to 2s2, 2p6, 3s2. So far we're at 2, 4, 10, 11, 12. And then our last 3 go into that p orbital. You can either do that first, or you can do the orbital diagram first. Some people prefer doing the diagram first because it lets them visualize it and then go back and write the configurations. Then they go, okay, I'm going to start drawing boxes. I know I'm going to need 1s, 2s to 2p. And they might go, okay, wait. They go, wait, I have 15, so that means, okay, 1s fills up first. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then they go, oh, okay, now I see how it's done, and then you can go ahead and write your configuration. So the last electron is in the 3p orbital. So that is an n equals 3. And since this is p, L equals 1. So remember, s equals 0, L equals 1. Or I'm sorry, s is 0, p is 1, d is 2. So that means the ml value could be -1, 0, or +1. These are degenerate, so any of them are correct. And then these are unpaired electrons, so we go ahead just by convention and say they're all +1/2. So our m sub s is +1/2. Now we can use the periodic table to identify elements by using the S, P, D, and F block. And this is something not in your book. Woo! So for those of you that are watching this, this will hopefully be a time saver for you. So if you remember, we have S block, D block, F block, and P block. And you can use these numbers, or these letters, and the period number to figure out some configuration information. So the period numbers are your N's. These are your energy levels. Okay? And for the D block, the energy level you're given -1 is your valence, is your valence shell. Okay, because even though you first fill up the S, like you go to 4S before you go to 3D, okay, your last shell that you fill is the D, is the D block, okay? So these are n minus 1, or your period number minus 1. And then your F block is n minus 2. Okay, or your period number minus 2. For the S block and P block, it's just that same number. Now, let's say we have some examples. We want to figure out the atoms from the electron configurations we're given. We start with argon, we go to 4s2, 3d5. So this 3d5, this is where we're ending. So this tells me D block, and it's the 5th element. Ha. So I go to D block, that starts here at scandium. Okay, and I also know that my highest value is 4. So n minus 1, 4 minus 1, 3 is where I'm going to be ending in 3D. Okay, but notice 4 here also for my highest energy. So I go, okay, 1, 2, 3, 4, 5. And then we see that matches up, 4s2, 3d5. We have manganese. For B, we're told krypton, 5s2, 4d10, 5p6. All right, so this guy, we have a 4d10. Oops, forgot to turn my page. And then we also see, though, that this D block is full. So our valence is the 5, is n equals 5. So n equals 5. And we're ending in P block at P6. So we're going to go ahead and go across to 5 to the start of P block, which is at indium. And we go 1, 2, 3, 1, 2, 3, 4, 5, 6. And we land on xenon. So you can use that last bit of your information to get your electron configuration. And just to kind of reiterate with the manganese one, 3d5, so that means if I take this 3 plus 1, that gets me period 4, or n equals 4. Okay, and that's how we know this period. So that makes life a little easier for identifying an element if you don't feel like trying to look everywhere on your periodic table to figure out what it's trying to tell you. Okay, so a little bit more on our configurations and the periodic table. Like we were saying, the atoms are arranged so that the elements that have the same chemical and physical property or similar properties are in the same group. So these guys have similar valence electron configurations, like we saw for group 1 and group 2. And again, valence electrons are what play the most important role in our chemical reactions, which is why elements in the same group have similar reactivity, because they have the same valence electrons. So a little bit more with the periodic table. We have what are called the main group elements, or the representative elements. And these are electrons where the last electron is either in an s or a p orbital. So these are s block plus p, or p block. The valence electrons are the ones that have the highest n. Okay, gallium, for example, ends in 4p1. And it has a total of 3 valence electrons, not the 3d, that's not part of the valence shell, but the highest energy level, which is 4, is. So we have 2 from the s, 1 from p, so it has 3 valence electrons. Okay, that filled 3d orbital, these are core electrons, not valence electrons, but they do not go in with argon, for instance. They don't go into the abbreviation here because argon does not have a 3d10 orbital. Now, our transition metals are metallic elements where the last electron enters a d orbital. So it goes to the s orbital, and on the energy level higher and then comes down to the lower energy level for D, though it's higher in energy value, lower in orbital number. Okay, so the valence electrons include the s orbital and the d orbital electrons. So vanadium, for instance, it goes argon 4s2 3d3. Both the 4s and the 3d electrons are part of its valence. So that's a total of 5 valence electrons. The inner transition elements or metals are the ones below the periodic table. I know I always want to call the main transition metals the inner ones because they're actually in the periodic table, but nonetheless, technically these ones are from inside the table. We just pull them out for space saving and to show that it's a different orbital block. Nonetheless, the electron occupies an f orbital, the last electron. So their valence electrons include the s, the f, and if present, the d subshell, only if it's there. So promethium, as an example, goes up from argon to 6s2 4f5. So the s shell is part of it. That means it has 7 valence electrons. Notice promethium does not have a d subshell. So when you get up in these higher electron counts, it's really helpful to use either the electron energy diagram or the one of the two energy diagrams that I showed you to figure out how things are going to fill up first. So this is another example. I know I kind of showed you the names SP, D, and F block. I just wanted to give you another visual example so you can see how it looks again. This was borrowed from lumenlearning.com. I thought it was a nice visual of the blocks. So we also have electron configurations. We can do these for ions. So remember, ions are formed when an atom either gains or loses electrons. And as I'm pretty sure none of you will ever forget that a cation is formed when electrons are removed from the atom to make it positively charged, because cats are good. Yay, kitties. Don't judge my drawings. For main group elements, the electrons that are added last are the first ones to be removed. Okay, so those valence electrons, like the s shell from a metal, are the first, or from like group 1 or 2, come off first. From transition metals and the inner transition metals, the ns electrons are lost first, and then the d electrons, and then or the f. So the ns go first. So if you go, 4s2 3d5, you're going to lose those s electrons before you lose the d electrons. For anions, these, just a refresher, form when an electron is added to our atom. And the way that we add them is we use the Aufbau principle, where we start off where all the electrons stay unpaired, and then they pair up as we start filling up the orbital. So let's look at some examples to predict some electron configurations. And we want to figure them out for sodium +1, phosphorus -3, aluminum 2+, Fe 2+, and Sm 3+. So what we should do first is we need to write the electron configurations out of the non-ionized atom, and then we're going to go ahead and take electrons off to do the ionization. So let's go ahead and write our electron configurations of the unionized atoms first. So for sodium is going to be 1s2, 2s2, 2p6, 3s1. And since it's +1, that means it's going to lose 1 electron, and it's going to come off of its outermost highest energy level, which is the 3s, so that 1 electron is coming off. So this becomes 1s2, 2s2, 2p6. Phosphorus normally has 15 electrons, so it would be 1s2, 2s2, 2p6, 3s2, 3p3, and we're gaining 3 electrons, and they're going to go into our outermost shell using the Aufbau principle. We can fit 3 more electrons in the 3p orbital, so that's where they're going to go. 1s2, 2s2, 2p6, 3s2, 3p6. Aluminum plus 2 is next. So it starts off. Aluminum has 13 electrons. 1s2, 2s2, 2p6, 3s2, 3p1. And we're doing with a positive 2. So that means it's going to lose electrons from our outermost shell. So it's going to lose one. It's going to lose the 3p, and then 1 from 3s, since our p orbital then is empty. So we have 1s2, 2s2, 2p6, 3s1. Next up, iron. So iron, to start off, is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now, we have iron plus 2. So we're losing 2 electrons, and this is a transition metal. So that means that those electrons are going to come from the s orbital first, not the d orbital. So they're going to come off from this 4s2, and we're losing 2, so that's where they're coming from. Just both of them. So now this leaves us 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And lastly, samarium plus 3. This guy's got a long configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then 4f6. That's a heck of an electron configuration. And then it is plus 3. So it is first going to lose its electrons from the s orbital. So from 6s. So there's our 2. And then it's going to now, since we need to lose 1 more, it's going to lose it from the f orbital. So it's all this stuff, and then 5p6 for f5. I am just not writing all that again. Here's all that information again for you. Just written a lot prettier than I did. So I hope this is making sense for you. If you weren't sure where I was getting these diagrams, remember the number of electrons is equal to the atomic number, and that's for all the electron orbital configurations that we did first, and then we took off or added electrons as we needed to get the proper number for our specific ions that we were looking at.